Welcome to our exploration of LeetCode problem number 2044, count number of maximum Bitwise-OR subsets. In this problem, we aim to determine the number of subsets of a given array that yield the maximum possible bitwise-OR value. We'll break down the problem, analyze potential approaches, and uncover the most efficient solution. Let's dive in. In this problem, we are tasked with finding the number of subsets that achieve the maximum bitwise-OR value from a given integer array nums. A subset is any combination of elements from the array, including individual elements or the entire array, but excluding the empty set. The bitwise-OR of a set is calculated by applying the OR operator across all its elements. For example, the bitwise-OR of the set 1, 2, 4 is 1, 2, 4 equals 7. Our goal is to determine the maximum possible bitwise-OR value across all subsets and then count how many subsets achieve that value. The input to the problem is an integer array nums, and the output is a single integer representing this count. Let's look at the first example to understand this better. If we have nums equals 3, 1, the subsets we can form are 3, 1, and 3, 1. Calculating the bitwise-OR for each subset, we find that 3 results in 3, 1 results in 1, and 3, 1 results in 3, 1 equals 3. The maximum bitwise-OR value here is 3. Among the subsets, 3 and 3, 1 both achieve this maximum value, so the output is 2. This example illustrates how we calculate the maximum bitwise-OR value and count the subsets that achieve it. Now for the second example, where nums equals 2, 2, 2. The subsets we can form are 2, 2, 2, and 2, 2, 2, along with all other combinations of non-empty subsets. In this case, the bitwise-OR for all subsets is always 2, because every subset contains the identical value 2, and the OR operation with itself does not change the result. The maximum bitwise-OR value is 2, and since all 7 non-empty subsets achieve this value, the output is 7. This demonstrates how identical elements in the array influence the result. In the third example, we have nums equals 3, 2, 1, 5. The maximum bitwise-OR value that can be achieved is 7, which is obtained by ORing the elements in specific subsets such as 3, 5, or 2, 5, 3. There are 6 subsets in total that achieve this maximum OR value. Calculating these subsets involves considering all combinations and determining which ones produce the value 7. This example highlights how distinct values in the array contribute to the maximum OR value and the importance of examining all subsets to count the ones that meet the criteria. There are a few edge cases to consider. First, if the array contains only one element, the result is always 1 because the single subset containing that element achieves the maximum bitwise-OR. For instance, if nums equals 10, the output is 1. Second, if all elements in the array are identical, all non-empty subsets will achieve the same OR value, and their count will be 2 n 1, where n is the size of the array. For example, with nums equals 2, 2, 2, the output is 7. Lastly, if the array contains distinct large values, such as powers of 2, the maximum OR value is obtained by ORing all elements, and the result depends on the number of subsets achieving that value. For instance, with nums equals 1, 2, 4, 8, the OR value is 15, and the subset combinations achieving this need to be carefully counted. To solve the problem of counting the number of subsets that achieve the maximum bitwise-OR value, we first consider a brute force approach. The idea here is to generate all possible non-empty subsets of the array nums, compute the bitwise-OR for each subset, and then track both the maximum OR value and the number of subsets that achieve it. To do this, we can use techniques like bit masking or recursion to generate all 2 n 1 non-empty subsets. For each subset, we calculate its bitwise-OR, compare it to the current maximum, and update the count accordingly. However, this approach has significant drawbacks. Generating all subsets is computationally expensive, taking 2 to the power of n time, and each OR computation for a subset adds another n. Combined, this leads to a total time complexity of 2 to the power of n*n, which quickly becomes impractical as the size of the array increases, especially for n greater than 15. This exponential growth in subsets makes the brute force approach infeasible for larger inputs. A more optimized strategy involves using backtracking with pruning. Here, instead of generating all possible subsets up front, we explore subsets recursively while maintaining the current or value. This approach avoids redundant computations and is designed to be more efficient than brute force. The key insight is that Bitwise-OR is idempotent, meaning adding an element to a subset either increases the OR value or leaves it unchanged. This property allows us to prune certain recursive branches when further exploration won't yield any new results. As we recurse, we keep track of the current OR value for each subset. If this value exceeds the global maximum, we update the maximum and reset the count to 1. If the current OR matches the global maximum, we increment the count. While the worst-case complexity can still be 2 to the power of n, the pruning mechanism significantly reduces redundant calculations, making this approach faster in practice. Overall, backtracking strikes a balance between computational efficiency and simplicity. Another approach worth considering is dynamic programming, which uses a table to track reachable OR values at each step. The idea is to iteratively update the set of possible OR values as we process each number in the array. We start with the OR set containing only 0. For each number in nums, we calculate new OR values by combining the current number with all existing values in the set, effectively simulating the inclusion of the number in various subsets. At the end of this process, the highest OR value in the set represents the maximum achieved, and we can count how many subsets contribute to this maximum. While this approach has its advantages, such as being potentially faster for small arrays, it also has limitations. The number of unique OR values can grow exponentially, making the approach memory-intensive for larger arrays with diverse numbers. This trade-off needs to be carefully considered depending on the problem constraints. In weighing the pros and cons of these strategies, we find that the brute force approach, while straightforward and easy to implement, is highly inefficient due to its 2 to the power of n*n time complexity, making it unsuitable for larger inputs. The dynamic programming approach is insightful and can perform well for small arrays, but it struggles with memory usage when the array has a large number of unique OR values. Backtracking with pruning, on the other hand, offers a practical middle ground. By leveraging the idempotent nature of the Bitwise-OR operation, it reduces redundant computations, making it both efficient and intuitive to implement. This balance of clarity, efficiency, and resource management makes the backtracking approach the most practical and scalable solution for solving this problem. In this problem, we are tasked with determining the maximum Bitwise-OR value that can be achieved by any subset of a given array, nums, and counting how many subsets reach that maximum value. To solve this, we use a brute force approach where we systematically generate all possible subsets of the array, compute the Bitwise-OR for each subset, and then count the ones that achieve the maximum OR value. The input to the problem is an array of positive integers, while the output is the count of subsets that give the maximum OR value. Now, the Bitwise-OR operation itself is critical to understand. It combines two binary numbers, setting a bit to 1 if that bit is 1 in either number. For instance, the OR of 5, binary 101, and 3, binary 011, results in 7, binary 111. It's also important to note that the OR operation is monotonic, meaning adding more elements to a subset can only increase or maintain the OR value, it never decreases it. The next step is to generate all possible subsets of nums. This can be achieved using the power set approach, where for an array of n elements, there are 2n possible subsets. Bit masking is a particularly efficient way to represent these subsets. Using an n-bit binary number, each bit represents whether a corresponding element in the array is included in the subset, 1, or excluded, 0. Once we have the subsets, we compute the Bitwise-OR for each one by iterating through its elements and applying the OR operation. Along the way, we track the maximum OR value encountered. To count the subsets achieving this maximum, we maintain a counter. If the OR of a subset matches the maximum value, we increment the counter. Finally, after processing all subsets, we return this counter as the result. Using bit masking to generate subsets is advantageous because it avoids recursion and maps directly to the binary representation of subsets, making it both simple and efficient. Another key insight is the monotonicity of the OR operation. Since adding elements to a subset can only maintain or increase its OR value, larger subsets will never have a smaller OR than their smaller counterparts. This property also provides an opportunity for optimization. For example, if a subset's OR value already matches the known maximum, we could terminate processing for that subset early. However, in the brute force approach we're discussing, we do not use this optimization. The data structures involved in this algorithm are straightforward: an array to store the input, counters to track the maximum OR and the number of subsets achieving it, and an integer to represent each subset as a binary number for bit masking. Let's consider a detailed example with nums equals 3, 1. The subsets of nums are 3, 1, and 3, 1. For each subset, we compute its bitwise OR. The empty subset has an OR of 0. The subset 3 has an OR of 3, and 1 has an OR of 1. The subset 3, 1 combines 3 and 1, resulting in an OR of 3. The maximum OR value across all subsets is 3. Now, we count the subsets that achieve this maximum. In this case, the subsets 3 and 3, 1 both have an OR of 3, so the count is 2. The algorithm then returns this count as the result. In terms of complexity, generating all subsets takes 2 to the power of n, because there are 2 n subsets. Computing the OR for each subset involves iterating through its elements, which in the worst case takes n. Thus, the total time complexity is n*2 to the power of n. Space complexity is minimal at 1, as we only use counters and bit masking without additional data structures. This implementation solves LeetCode problem number 2044 by recursively generating all subsets of the given array nums and calculating their bitwise OR values. The goal is to count how many subsets achieve the maximum possible bitwise OR value. First, the max_OR variable is computed by iterating over all elements in nums and performing a cumulative bitwise OR operation. This gives the maximum bitwise OR value that any subset can achieve. Next, the DFS function is defined to explore all possible subsets using recursion. It takes the current index in the nums array and the current cumulative OR value as arguments. The base case for the recursion is when all elements have been considered, i.e., index = len, nums, at which point the function checks if the current OR value matches max_OR. If it does, the function returns 1, indicating that this subset achieves the maximum OR, otherwise, it returns 0. For each element in the array, the function considers 2 possibilities, including the element in the current subset, updating the OR value, or excluding it. These 2 recursive calls are combined to count all subsets that achieve the maximum OR. Finally, the DFS process is initiated from index 0 with an initial OR value of 0, and the total count of subsets meeting the condition is returned. This approach ensures that all subsets are explored, making it a comprehensive solution for the problem. Here, we start by importing the necessary libraries and defining our solution class. The goal of the method countMaxOR subsets is to calculate the number of subsets of the given array nums that achieve the maximum bitwise OR value. To do this, we first calculate the maximum possible bitwise OR for the entire array. This is done by iterating through each number in the array and applying the bitwise OR operation cumulatively to the variable maxOR. After determining the maximum possible OR, we initiate a depth-first search using a helper method called DFS. This recursive function will explore all possible subsets of the array, starting from index 0 with an initial OR value of 0. The goal is to count how many of these subsets achieve the maximum OR value that we just calculated. The DFS method is where the recursive exploration happens. First, we handle the base case. If the current index equals the length of the array, it means we've considered all the elements. At this point, we check if the current OR value matches the max OR. If it does, we return 1, indicating that this subset contributes to the count. Otherwise, we return 0. Next, we explore 2 possibilities for the current element, including it in the subset and excluding it. If we include it, we perform a recursive call with the OR of the current value and the current element. If we exclude it, we make a recursive call without altering the OR value. Finally, we return the sum of these 2 results, combining the counts from both the inclusion and exclusion cases. This way, the function systematically evaluates all potential subsets to determine how many achieve the maximum OR value. To solve this problem, we start with the array nums equals 3, 1. The first step is to calculate the maximum bitwise OR value for the entire array. To do this, we iterate through the elements and perform a bitwise OR operation cumulatively. Initially, max_OR is 0. When we include the first element, 3, the calculation is 0, 3, which results in 3. Then, adding the second element, the calculation becomes 3, 1, which still results in 3. So, the maximum or value for the array is 3. Next, we begin our depth-first search, or DFS, to explore all possible subsets. The DFS starts at index 0 with an initial or value of 0. At index 0, where the value is 3, we have two choices: include it in the subset or exclude it. If we include it, the OR becomes 0, 3, which is 3, and we proceed to the next index. If we exclude it, the OR remains 0, and we also move to the next index to explore further possibilities. At index 1, the value is 1. Again, we have two choices. If we are in the case where the OR is already 3, from including 3 earlier, we can include 1, which results in 3, 1, but this remains 3. Alternatively, we can exclude 1, and the OR stays 3. On the other hand, if the OR was 0, from excluding 3 earlier, including 1 results in 0, 1, which gives 1. Excluding 1 keeps the OR at 0. Once we reach index 2, which is beyond the last element of the array, we hit the base case. Here, we check whether the current_OR equals the max_OR, which is 3. For the paths where the OR is 3, we count the subset as valid and return 1. If the OR is not 3, we return 0. Summing up all valid paths, we find that there are two subsets where the OR equals the maximum, 3, and 3, 1. Now, let's consider another example where nums equals 2, 2, 2. The first step remains the same: calculate the maximum or value. Since all elements are 2, the OR accumulates as 0, 2, which gives 2, and remains unchanged no matter how many times we include additional 2s. So, the max_OR for this array is 2. Next, we start the DFS. At index 0, we have two options: include the first 2, resulting in an OR of 2, or exclude it, keeping the OR as 0. At index 1, for the path where the OR is already 2, we can include or exclude the second 2, but the OR remains 2 in both cases. For the path where the OR is 0, including the second 2 changes the OR to 2, while excluding it keeps the OR at 0. When we reach index 3, which is the base case, we check if the current_OR equals 2. Any path with an OR of 2 is valid, so all calls to DFS 2, 2 return 1. Summing up all valid paths, we find that there are 7 subsets where the OR is equal to 2. These subsets include 2, 2, 2, 2, 2, 2, and others formed by excluding certain elements. Now, let's explore the example nums equals 1, 2, 4. The first step is to compute the maximum or value. Starting with 0, 1, we get 1. Adding 2 results in 1, 2, which is 3. Finally, including 4 gives 3, 4, which is 7. So, the maximum or value for this array is 7. Starting the DFS at index 0, including 1 gives an OR of 1, while excluding it keeps the OR at 0. At index 1, if the OR is 1 from including 1 earlier, we can include 2, resulting in an OR of 3, or exclude it, keeping the OR at 1. For the path where the OR is 0, including 2 changes it to 2, while excluding it keeps it at 0. At index 2, we continue exploring by including or excluding 4. Anytime the current_OR equals 7, we count the subset as valid. Summing up all valid paths, we find 6 subsets that achieve the maximum or value of 7. These include 1, 2, 4, 2, 4, and others. The key insights from these examples are that DFS systematically explores all subsets by making inclusion and exclusion decisions for each element. The pre-computed maximum or value allows us to prune unnecessary paths. Finally, the base case ensures that we only count subsets matching the desired OR value, making the approach both correct and efficient. The time complexity of this solution is primarily driven by the depth-first search, or DFS, approach used to explore all possible subsets of the input array nums. To understand this, let's break it down step by step. First, the total number of subsets of an array with n elements is 2n, because each element has two choices. It can either be included in a subset or excluded. This means there are 2n combinations in total. The DFS function is called recursively for each of these subsets, so there are 2 n recursive calls overall. Now, within each of these calls, the algorithm calculates the bitwise-OR for the current subset. The bitwise-OR operation between two integers is a constant time operation, or O1. Since this operation is performed during every recursive call, the total cost of these operations is proportional to the number of calls, which is also 2 n. When we combine these factors, the overall time complexity of the solution is O2 to the power of n. Now, let's move on to the space complexity of this solution, which is influenced by the recursion stack and any additional memory used. First, consider the recursion stack. The maximum depth of the recursion corresponds to the number of elements in the array n, because the DFS processes one element per recursive level. Therefore, the memory used by the recursion stack is proportional to n, giving us a space complexity of O(n) for this part. Next, let's look at additional storage. In this specific implementation, no extra storage structures, such as arrays or lists, are used to keep track of subsets. This means that there is no additional memory overhead beyond the recursion stack. Combining these two factors, the overall space complexity is O(n). As for the best, average, and worst-case scenarios, both the time complexity and space complexity remain consistent. The algorithm explores all subsets regardless of the input values, so the time complexity is always O2 to the power of n, and the space complexity remains O(n) in all cases. To put this into perspective, let's compare the DFS approach with a brute force method. A naive brute force solution would explicitly generate all subsets, calculate their bitwise-OR values, and then count how many of those subsets achieve the maximum OR. While this brute force approach has the same time complexity of O2 to the power of n, due to the number of subsets, it would require significant additional space to store all the subsets, leading to an O2 to the power of n space complexity. In contrast, the optimized DFS approach avoids storing subsets altogether. Instead, it tracks only the current OR value during traversal, which reduces the space usage to O(n) for the recursion stack. To understand why the time and space complexities have these values, note that the 2 n subsets come from the fact that each of the n elements has 2 choices, include or exclude. The recursion stack depth corresponds to n, as one element is processed per level of recursion. Additionally, the OR operation is performed in constant time, so it does not contribute to a higher asymptotic complexity. This is why the time complexity remains O2 to the power of n, and the space complexity is O(n) for this approach. One of the most common mistakes when tackling this problem is misunderstanding the process of subset generation. Generating all subsets of an array is a foundational step, but it's easy to either skip subsets accidentally or generate duplicates, especially for beginners. Using tools like recursion or libraries such as itertools can simplify this process, but it's important to ensure completeness and accuracy. Another frequent error is incorrect calculation of the bitwise-OR. Some might mistakenly use addition or multiplication operators instead of the bitwise-OR operator, which is represented by. For example, confusing a b with a plus b will lead to completely incorrect results. Additionally, edge cases can trip up implementations. Scenarios like an empty array, all elements being identical, or a single element input are worth testing thoroughly. Lastly, inefficiency is a major pitfall for larger inputs. Since the number of subsets grows exponentially with the size of the array, exhaustively generating subsets without optimization can lead to timeouts. Techniques like pruning or memoization are essential to handle large inputs efficiently. A deeper understanding of bitwise properties is crucial for solving this problem effectively. The bitwise-OR operation combines elements in specific ways, and misusing or misunderstanding these properties can result in redundant calculations or overlooked subsets that maximize the OR value. From an interview perspective, this problem is a great test of your bitwise operation skills. Operators like AND, OR, and XOR are common topics, so practicing how they combine numbers is invaluable. Optimization is another key focus. While brute force methods might work for small inputs, interviews often require you to discuss and implement scalable solutions for larger constraints. Leveraging the properties of bitwise-OR can help reduce unnecessary calculations. Additionally, proactively discussing edge cases like empty arrays or large inputs with repeated elements can set you apart. For subset enumeration, there are several techniques to explore, including recursion, backtracking, and bit masking. Bit masking, in particular, is highly efficient for this problem and worth highlighting in discussions. This problem shares similarities with several related challenges that can help you build the required skills. For instance, LeetCode problem 78, subsets, focuses on generating all subsets of an array, which is a foundational technique for this problem. Another useful problem is LeetCode 1310, XOR queries of a subarray, which deals with bitwise operations, though it focuses on XOR instead of OR. LeetCode 90, subsets 2, is a variation of the subset generation problem that introduces the complexity of handling duplicates, making it a valuable exercise for careful subset handling. Finally, LeetCode 137, single number 2, revolves around bitwise operations to identify unique numbers in an array, sharpening your intuition for bit manipulation. Exploring these problems can deepen your understanding of subset enumeration and bitwise operations, both of which are essential for mastering this challenge. There are multiple approaches to solving this problem, each with its own trade-offs. The brute force approach involves generating all possible subsets, calculating their OR values, and counting the subsets that match the maximum OR. While this method is simple and straightforward, its time complexity of O(2 to the power of n*n) makes it impractical for larger inputs. A more efficient option is optimized backtracking. This approach generates subsets dynamically while keeping track of the current OR value, allowing you to prune branches that cannot achieve the maximum OR. Although faster than brute force, it requires careful implementation to avoid redundant calculations. Another powerful method is bit masking, where subsets are represented as integers, and OR values are computed directly. This avoids recursion and is often more efficient. However, bit masking requires a solid understanding of bit manipulation, making it a clean but slightly more advanced technique for subset enumeration. Dynamic programming, or DP, offers another alternative for solving this problem. With DP, you can maintain a table to track all achievable OR values as you iterate through the elements of the array. This method systematically updates the table to build on previously computed results. While it requires more complex implementation than other approaches, DP can significantly reduce redundant calculations. By leveraging previously computed states, you avoid recalculating results for overlapping subsets, making it a powerful optimization technique for this problem. Although challenging to implement initially, mastering DP for such problems can greatly enhance your efficiency in solving similar challenges. Thanks for sticking with us as we tackled LeetCode problem number 2044, count number of maximum Bitwise-OR subsets. We reviewed the problem statement, analyzed key concepts like bitwise operations and subsets, and discussed an efficient approach to solve it. If you found this explanation helpful, please like, subscribe, and stay tuned for more problem-solving content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!